Welcome to a refresher lesson for finding zeros of polynomial functions. As this topic is a bit complex, I have broken it into two parts. This video will focus on finding all zeros and corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. The other part reviews finding real zeros and can also be found at Teachers Pay Teachers and on my YouTube page. In this video, I will explain the skills and steps necessary to complete all of the examples on the Finding All Zeros worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So before we get into actually finding these zeros, again, we need a bit more information that's going to inform how we go about this. So the first two theorems that are going to be helpful, the first one is called the Fundamental Theorem of Algebra, which sounds like it should be earth-shaking, really intense kind of, wow, this is the answer to all mathematics kind of thing. But it's really pretty simple. It basically says that every polynomial has at least one zero in the complex numbers. So linears, quadratics, whatever degree you can think of, there's always at least one zero in the complex numbers. And keep in mind that the complex numbers mean it could be the real numbers or the imaginary numbers, because reals are part of that complex number set. So it's basically saying that every polynomial has to have a zero of some kind. Okay, then we have the linear factorization theorem, which states that every polynomial, again, in sort of just this generalized polynomial form, showing you the different terms that might make up the polynomial. If you have a function that is a polynomial function, then every polynomial can be factored as f of x equals some a value times x minus c sub 1 times x minus c sub 2, repeated for as many factors as you need. So the fundamental theorem of algebra is telling us that there's always at least one zero, and then linear factorization theorem is telling us that we can use those zeros to come up with factors and rewrite the polynomial in a factored form. Now, if we put these two together, what this tells us is that every polynomial has exactly n zeros among the complex numbers. So again, reals, imaginaries, whatever. The n represents the degree of your polynomial. So whatever the degree of your polynomial is, that's how many total zeros that your polynomial has to have. It can be positive or negative real zeros. It can be real zeros or imaginary non-real zeros. And if you have a zero that has a multiplicity that's greater than 1, each of those zeros gets counted separately to add up to whatever the degree is. So that can be really helpful for us as we start looking for all of the possible zeros for a polynomial function. There's also a trick, a tool, I guess, called Descartes Rule of Signs that can help to delineate a bit more as to what those zeros might be. And the way this rule of signs works is that, again, if we have this polynomial in a general form with real coefficients, we've got to make sure that that is a true feature of our polynomial. Then the number of positive real zeros is either equal to the number of sign changes of your function, or is less that number of sign changes by an even integer. Similarly, for the negative real zeros, That's also going to be equal to the number of sign changes, but this time it's of the f of negative x. So for positive, you're using the original function that was given to you. For the negative real zeros, you are substituting a negative x into each of the terms, simplifying to find out what that new function would be, and then looking at the number of sign changes in that function. And again, your negative real zeros will either be equal to that number or less than that number by an even integer. So how do we do that? What does that all mean? So let's talk about it. So we want to use Descartes' Rule of Signs to determine the possible number of positive and negative real zeros for the polynomial f of x equals 2x to the fourth minus 10x cubed plus 11x squared minus 15x plus 12. So for positive real zeros, we are going to use this original f of x. Make sure again that it is that your polynomial is written with exponents in descending order. And then just as you read from left to right, if you see a sign change, you count it. So here we're going from a positive 2 to a negative 10. So that's one sign change. Then we go from a negative 10 to a positive 11. So there's another one. From a positive 11 to a negative 15 is another one. And then a negative 15 to a positive 12. So there are 1, 2, 3, 4 sign changes in this function. So what this means then, if we're looking at positive real zeros, we are either equal to that number of sign changes or less than that number by an even integer. So that means I either have 4 real zeros, I could have 2 real zeros, or I might not have any real zeros. Each of those is a possibility for this function. Now we'll explain why in just a second, but that's what the rule says. Now, for the negative real zeros, we need to find f of negative x. So we are going to substitute negative x in for each of the x's. And then we're going to simplify. So if I take negative x to a fourth power, it's going to end up being a positive x to the fourth. So this term remains 2x to the fourth. If I take negative x to a third power, that's going to become a negative x cubed times the negative 10 means it's going to turn to a positive 10x cubed. Negative x squared, again, will give us a positive x squared times the positive 11, so that remains 11x squared. The negative x times the negative 15 will give us a positive 15x. And then we have our plus 12. Okay, so now if we look at sign changes, since everything is positive here, there are no changes. So since there are no sign changes, that means there are going to be 0 negative real zeros. And that can be really helpful when you're trying to find the zeros of your function, because if you make your rational list and you get this kind of result from Descartes' Rule of Signs, you know that you don't need to test any of the negative rational numbers because there are no negative real zeros. Okay. All right. One other thing that can be helpful is this idea of a complex conjugate theorem. And it says that if the polynomial function f of x has real coefficients and has one complex zero in the form of a plus bi, then we know we have to have the complex conjugate of that zero, the a minus bi, as a zero also. And so this is why you have that decreasing by 2 in the rule of signs, because if there are any complex zeros, they always have to happen as a pair. Okay, and you're going to count them as towards your total number. So your positive and negative real zeros are going to either be the number of sign changes or less than that by an even integer, because if there are complex zeros, they always happen as pairs. All right, so we're going to pull all of this together now using the rational zero theorem from the other video. If you're not sure about that, please check out the other video. The Fundamental Theorem of Algebra, the Linear Factorization Theorem, Descartes' Rule of Signs, and Complex Conjugate Theorem. We're going to use all of these tools that we now have to try to work as efficiently as possible towards finding all of the zeros for a polynomial function. These tools are going to help to focus our work and narrow down the possibilities of what those zeros might be. All right, so we have the problem that says list all the zeros of the function x to the fourth plus 2x cubed plus 22x squared plus 50x minus 75. First thing we're going to do is we're going to use the rational zeros theorem to make our list of possible rational zeros. So that's the P and Q. So P are the factors of my constant. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. And then for our Q, we're looking at the factors of our leading coefficient, which in this case is just 1. So we have plus or minus 1. So our P over Q list, since we have a Q of just 1, it ends up being simply the list of the P factors. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. Okay, then we're going to use Descartes' Rule of Signs. So I'm first going to look at the f of x, and I'm going to see we go positive for x to the fourth. We're still positive for x cubed term. We're still positive for the x squared term, positive for the x term, but we do have a change right here from positive to negative. So that means we're going to have one possible positive real zero, since there was just one sign change. And then we're going to find our f of negative x. And if you notice back in the example before, what really happens here is that only the exponents that are odd change signs from the original function. Because any of the exponents that are even though I put a negative x in, taking it to that even exponent turns it back to a positive. So it doesn't change that term from what it was originally. But with the odd exponents, those are going to change the signs. So I don't really have to write it all out like I did in that example. I can simply go and say, okay, x to the fourth, that's even, that will stay the same. X cubed, that's odd, that's going to change to the opposite sign. X squared, even, keeps the same sign. X, technically to the first power, so that's odd, that will change to an opposite sign, and then our constant stays the same. And so now, if I look, I have a positive to negative right there, negative to positive there, positive to negative there, and then negative to negative, which wouldn't count. So for the negatives, I have 3 sign changes, or less by an even integer, I might only have 1 negative real 0. So it could be 3, or it could be 1. All right, so from knowing that then, we're going to combine Descartes' Rule of Signs, those results, with that Fundamental Theorem of Algebra and the Linear Factorization Theorem to come up with a little table. And so for this table, we're going to have positive reals for one column. We're going to have negative reals for a second column. And then I'm going to call this non-real. Because if I call it complex, everything is complex. But I don't want to call it imaginary either because it may be a full A plus BI kind of complex. So I'm going to call it non-reals. And so I'm going to take these results and say, all right, so I could have 1 positive real with 3 negative reals. Well, remember the 2 theorems here together told us that whatever our degree is the total number of zeros we should have. So if I have a combination of 1 positive and 3 negatives, then in that case, there would be 0 non-reals. But I could also possibly have 1 positive with 1 negative. And if that's the case, then there are still 2 other zeros to be accounted for, and so those must be non-real zeros. So this just gives us kind of an organized way of looking at what the possible outcomes might be, so that as I start working, I'm not working on things unnecessarily. All right, so let's start doing the actual work. So we're going to start with our coefficients of 1, 2, 22, 50, and negative 75. If you look on a graph, you can see that it looks like our graph would cross the x-axis around 1. So let's test out the 1 first. And so with our synthetic division, I'm going to bring the 1 down, multiply, add, multiply, add, multiply, add, multiply, and add. So that's a good sign. We've got that remainder of 0. So we went from a 4th degree function now to a cubic. All right, this is cubic, and we want to keep going until we get to a quadratic. But notice this positive 1 that I have as a 0 now, there is only 1 positive real 0. So I don't need to try any of the other positive zeros from that rational zero list. So I need to start thinking about negatives now. And again, if you're able to look at a graph, it looks like there might be an x-intercept at about -3. So we're going to use the -3 now with that resulting quotient that we got. So bring down the 1, multiply, add, multiply, add, multiply, add. So there's another 0 remainder, which is good. That's what we want. And we now have a quadratic for our quotient in the form of x squared plus 25. So now if we set that equal to 0 and solve, we would get x squared equal to -25. X is going to equal plus or minus the square root of that -25, which is plus or minus 5i. So our zeros, I need 4 of them, remember, because this was a 4th degree polynomial, are going to be this 1, this -3, and then the plus and the minus 5i. And if we look on our chart, that fits this possibility. We had 1 positive, 1 negative, and 2 non-real zeros. So everything seems to fit. It makes sense. We're on the right track. Okay. All right. One other type of problem that I want to talk about quickly is what if we are asked to do basically the reverse of all of this? So instead of being given the polynomial function and asked to find the zeros or possibly the factors, what if we are given the zeros and asked to come up with what the function might be? So here's this example where we're asked to find a 3rd degree polynomial. So we know we want it to be cubic with real coefficients that has zeros of 5 and -2i and meets the criteria that f of 1 is equal to 10. So the first thing we want to do is actually use our complex conjugate theorem to notice that I have this complex imaginary root that's been given to me. And because of that, I automatically know that if -2i, which is technically 0 minus 2i, is one of my roots, then the complex conjugate also has to be one of my roots. So with this 3rd degree polynomial, I should be looking at 3 roots. They technically only gave me 2, but the complex conjugate helps me to figure out what that 3rd one should be. So -2i and +2i are both going to be zeros for this polynomial. So now I'm going to use the linear factorization, which said every polynomial can be rewritten as a times the factors x minus k. So x minus this 0 would be x minus 5. X minus this 0 will be x minus a -2i. And x minus this 0 will be x minus 2i. Okay, and so just to make things easier, this is really just x plus 2i. Now, if you are looking at factors that contain non-real zeros, I would highly recommend that you multiply those factors first. If you don't have any factors involved with these non-real zeros, then it doesn't really matter what order you multiply in. But with non-real zeros, you really should multiply those two together first, because if you do this correctly, all of the I terms should cancel each other out. And then the multiplying with the rest of your factors becomes a little more straightforward. So I'm going to take x times x, which is x squared. I've got x times negative 2i, so a negative 2ix. Then I've got my positive 2i times x for inside, so positive 2ix. And then positive 2i times negative 2i will be a negative 4i squared. So you can see the negative 2ix and the positive 2ix cancel out. So that gets rid of those terms that have i's in it. And remember, I squared is the same equivalent to negative 1. So this really becomes x squared plus 4. And then we still have the x minus 5 factor and some a value. So now we'll multiply these two factors together. So a is still out in front. X times x squared will be x cubed. X times 4, 4x. Negative 5 and x squared minus 5x squared. Negative 5 times 4 minus 20. Okay. Now, the missing piece here is this a value, and that's what this bit of information is for. If we know that substituting 1 in for x is supposed to give us a result of 10, we can use that to find our a value. So I'll substitute 1 in for x. And we know that has to equal 10. Let me continue our work up here. So I've got 1 plus 4 is 5, minus 5, 0, minus 20. So I end up with negative 20 times that a equal to 10. And now I can divide both sides by that negative 20, and I end up with a negative 1/2. So now I can put my final answer together. F of x equals negative 1/2 times, and then I'm going to write my polynomial with descending exponents. So I'll have my x cubed first, minus the 5x squared, plus 4x, minus 20. Now, depending on your teacher, depending on your textbook, they may want you to actually distribute your negative 1/2 through. So you could also have a negative 1/2 x cubed plus 5/2 x squared minus 2x plus 10. That would also be a proper answer. Okay, so in these cases, they will give you some zeros. You may need to determine other zeros using the complex conjugate theorem. And then they'll usually give you some other characteristic, like at a particular x value, you get this y value, or this is a particular y-intercept, meaning that when x equals 0, this is the answer you should get. And you can use that in your last step to find the a, and then write your final polynomial from that. Okay, I hope you found this helpful. If you would like to see the video for finding real zeros or other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.